Good morning, our dear valued audience. Welcome to our today's class. Today we intend to discuss with you elaborately the concept in mathematics called trigonometry here on the board. So the question is, what is trigonometry? Trigonometry is an aspect of mathematics that looks at the relationship between the length of the sides and the angles of a right angled triangle. It studies the relationship that exists between the length of the sides and the angles of a right angled triangle. So the question is, what is a right angled triangle? Which this concept studies the length of its sides to the angles suspended by what? By the triangle. So we give a sketch of what is meant by a right angled triangle. A right angled triangle can be drawn like this. A right angled triangle. It can be drawn this way. And I first of all want us to understand literally, by a way of definition, what a right angled triangle is. A right angled triangle is a type of a triangle where one of the included angle is 90 degrees and the sum of the remaining two angles is equally 90 degrees. In total, there are three angles that are contained in a triangle. These angles are 1, 2, and 3. So let me denote here with what? With beta. This sign here stands for right angle. So it tells us that here is already 90 degrees. So I can easily write here to be what? 90 degrees. And the total angle in a triangle is 180 degrees. So if here is already 90 degrees, it implies that the sum of this theta and beta must be equal to 90 degrees. That is, that beta degrees plus theta degrees must give me 90 degrees. So any triangle that is drawn in such a way that one out of its three angles is 90 degrees, while the sum of the two remaining angles is 90 degrees, is what we call a right angled triangle. Ordinarily, when a triangle is drawn, we use capital letters to denote the angles that are contained inside that triangle. Therefore, I can label here to be capital A, here to be capital B, and here to be capital C. What this A stands for is this beta degrees. What this C stands for is this theta degrees. And what this B stands for is this 90 degrees. Therefore, the capital letters written at the edges of a triangle stand for the angles that are contained inside the triangle. Of course, when we write the edges with a capital letter, we talk about writing the lengths with a small letter. And this small letter is going to be a small letter of the capital letter opposite to that line. What do I mean by this statement? This line A to B is opposite to this capital letter what? B. So I am going to write this letter what? Here small letter what? B. This length A to B is opposite to this capital letter C. So I'm going to write here with a small letter what? C. And this length B to C is opposite to this capital letter A. Therefore, I'm going to write with a small letter what? A. Therefore, line AC is B, line AB is C, and line BC is A. This is what we call a right angled triangle. Okay? And there are three basic trigonometric functions that exist about this right angled triangle. And those three trigonometric functions are what we call the sine, what we call the cos, and what we call the tangents. So we have what we call the sine, what we call the cosine, and what we call the tangents. Tangents. The short form of this sine is always written as this, S-I-N, sine. The short form of this cosine is always written as what? C-O-S, that is cos. While the short sign of this tangent is always written as what? As tan. And bear you in mind that when you talk about sine, you are talking about sine of an angle. You talk about cos, you talk about what? Cos of an angle. And you talk about tan, you talk about tan of what? Of an angle. So we can be talking about, with reference to this theta, we will be talking about what? Sin theta, cos theta, and tan theta. What are these three basic trigonometric functions telling us about? They are telling us the nature of the relationship that exists between the length of the sides of the triangle to the angle contained inside that triangle. And there is a relationship in form of an acronym that represents the kind of relationship that exists between the length of sides and the angle contained in the triangle with respect to these three basic trigonometric functions. And that acronym is called SOHCAHTOA. That acronym is called what? SOHCAHTOA. And what we mean by this SOHCAHTOA is this, that you are saying that the opposite of the triangle all over hypotenuse of the triangle is what? Sine. And adjacent all over hypotenuse is cosine, and opposite all over adjacent is tangent. Is what? Tangent. So we are going to find a way, we are going to study this thing very well with this triangle which we have written, making use of what we call SOHCAHTOA. So do me a favor, hold brief while I clean this what I have written on the board. Draw a right angle triangle while we use it now to study these three basic trigonometric functions with respect to this acronym SOHCAHTOA. So permit me to clean this. So I have a right angle triangle. And look at my right angle triangle. Look at it here. This is my right angle triangle. This is my right angle. Here I have my right angle, which stands for 90 degrees. Here I have my what? My theta. Here I have my what? My A, my B, and my C. And here I have my what? My beta. In degrees and in degrees. Here, of course, is my 90 degrees. Then here remains my small letter B. Here remains my small letter C. Here still remains my small letter what? A. Of course, the longest side of the triangle, which is opposite to the 90 degrees or to the angle 90, is what we call the hypotenuse. So B here is the hypotenuse. With respect to theta, the side where the theta is facing is the opposite. So theta is facing this C, So C is opposite. And then the remaining third side that is neither faced by the right angle nor by the theta is what we call the adjacent. So this my A is the what is the adjacent. So let us look at the cosine, look at the sine, and look at tangent with respect to what to theta. From the SOHCAHTOA, opposite to over hypotenuse is sine. So sine theta here, sine theta is opposite over hypotenuse. Where is my opposite with respect to this theta? It is what? C. Where is my hypotenuse? It is what? B. So I have what? C all over what? B. Then here am I for cos. So I'll be able to have that cos theta is given as adjacent over hypotenuse. Where is my adjacent here? My adjacent is A. Where is my hypotenuse? My hypotenuse is B. So I have what? A all over what? B. Then here am I for tan. So I have that tan theta is given as opposite all over what? Adjacent. Where is my opposite? C. Where is my adjacent? A. With respect to this theta, which is what we are talking about here. So it becomes what? My C all over what? A. So these are the values of sine theta, cos theta, and tan theta. Of course, there are other functions that exist which are just the inverse of these three basic trigonometric functions. We are going to look at them equally. Okay? Other three trigonometric functions, they exist, but they are simply the inverse of these trigonometric functions. And we are told that 1 over sine theta is given as cosec or cosecant theta. And this cosecant is often written in a short form as CSC of theta. So what you are saying is that 1 over sine theta is given as CSC of what? Of theta. We are equally told that 1 all over cos theta is given as secant theta. And it is always written as sec theta. And then we have that 1 all over tan theta is given as cot or cotangent theta, which is often written in a short form as cot theta. So how do we now see? We are now saying that CSC theta is 1 over sine theta. So this thing implies that I have that this equals. Here is my 1, I will write 1. This sign here means divide by. So I have divide by. Sine theta is already written as C all over B. So I have C all over what? B. And of course, when this thing changes to multiplication sign, denominator goes up and numerator comes down. And then this thing becomes what? B all over C. I come over to this one. So this one equals. Now we are told that the sec theta is 1 over cos theta. Here is my 1, so I will write 1. This sign here means what? Divide by. So I have divide by. Then my cos theta is already written here as A over what? B. So I'll just write what? A all over what? B, which is equals. When this division sign changes into multiplication sign, denominator goes up, numerator comes down. Then I'll have what? B all over what? A. Then here am I at what? Cot. Then we are told that this cot theta is 1 over tan theta. Look at my 1 here. So I will say this equals 1 divided by. My tan theta is already written as what? C all over what? A. So I have C all over what? A. And of course, my C over A, when this division sign changes into multiplication sign, denominator comes up, numerator goes down. I have what? A all over what? C. So, my cosec theta B all over C, sec theta B all over A, cot theta A all over C. We are going to bear this in mind and bear this in mind. So what I'm going to do is to bring my hand up here and be able to call up this thing which you have established and write here. So what I'm going to have here is I'll have, let me put an arrow here, and then put this semicolon here. So that I will call up this one. What we have here is that CSC equals B all over C. I have B all over C. Then sec, which is sec, this is theta. Theta is given as B all over A. So I have B all over A. And what I have as cot theta is given as A all over C. We have established this. We have established what? This. Okay? So what are we now going to do now? I want us to equally now look at, permit me now to clean here because we have called up whatever thing we drive from here to here. The essence of this 1 over sin theta is to arrive at this, which is what we have here. The essence of this 1 over cos theta is to arrive at this, which is this, and which is what we have on this. And the essence of this 1 over tan theta is to arrive at cot theta, which is this, and which I've called up here. So permit me now to clean this particular place. I want us to look at what exists when we divide one basic trigonometric function by the other. That is, when I say sin theta divided by cos theta, what do I get? What does it look like? When I say cos theta divided by sin theta, what do I get? What does it look like? Is it something that can help us? That's what we want to look at now. So I'll come here and I'll write the first one. The first one says sin theta all over cos theta. This equals. Sin theta is C all over B. So I have C all over what? B. This sign means what? Divide by. So I have divide by. Cos theta means what? A all over B. So I have what? A all over what? B. Of course, in mathematics, when this division sign changes to multiplication sign, what I am going to have is that this B goes up and this A comes down. And what I have becomes C all over B multiplied by B all over what? A. There is B here and there is B here, so they can cancel. I'll cancel this and cancel this. What is remaining is what is C over A. So this is equal to C all over what? A. Let us come back here and closely look at what we have on the board. We had sin theta to be C over B. We had cos theta to be A over B. We had tan theta to be C over A. And what we have here is C over A. What gave us this C over A? Sin theta all over cos theta. So by implication, if tan theta equals to C over A and sin theta all over cos theta equals C over A, it implies that tan theta equals sin theta all over cos theta. That one is established. So we need to include it here. So we now come here and say that sin theta or tan theta equals sin theta all over cos theta. We have established that one. Then let us divide this by this and see what we are going to get. So permit me to clean this one we have done here on the board. I now come over here and I will say cos theta all over sine theta. What will it give us? How can it help us? B is equals. Cos theta means what? A all over B. So I have A all over B. This sign means divide by. So I have divide by. Sin theta means what? C all over what? B. I have C all over what? B. Changing this thing into multiplication sign, I have A all over B multiplied by B all over C. So that this B can cancel this B. And what I have becomes what? A all over what? C. We come back. While we have sin theta is C all over B, it is not the same thing with this. What we have cos theta is A over B, it is not the same thing with this. What we have tan theta is C all over A, it is not the same thing with this. What we had here is cosec theta is B all over C, it is not the same thing with this. Sec theta is B all over A, it is not the same thing with this. Cot theta is A over C, and this is A over C. So if cot theta is A over C, it implies that cos theta all over sin theta is cot theta. In as much as cot theta is A over C and cos theta all over sin theta is A over C. It means that this and this are the same thing. In as much as this gave this quantity and this gave this quantity. So I will now add here equally that cot theta is given as cos theta all over sin theta. With this in mind, we are going to do a lot of things. And what are we going to use this thing to do? That will be helping us on the course of the study of this concept, trigonometry. There are a lot of challenging questions that are under this topic. I saw them. I didn't like to call them up. Not until when we establish these relationships, be able to have them at the tip of our fingers. Then we now go into solving problems. By then, you find out what are today's lesson, or you find out the relevance of our today's lesson. The only thing I want you to do for me for now is remembering that we had a right angle triangle, and from this right angle triangle, we looked at the three basic trigonometric word function that relates the length of the sides of a triangle to its angle. The first one is sin theta, which is opposite of our hypotenuse here. The second one is cos theta, which is adjacent of our hypotenuse. Look at it here. The third one is tan theta, which is opposite of our adjacent, coming from that SOHCAHTOA. Having established these three basic trigonometric functions, coming from this acronym, SOHCAHTOA, we decided to look at the inverse of these trigonometric word function. And we said that 1 all over sin theta is known as what? Cosec theta. 1 over sin theta is known as what? Cosec theta. Written in form of abbreviation this way and given as what? B over C. In as much as we are talking about 1 over something, and this sin theta is already C over B. If you say 1 all over C over B, you will now have B all over C. We are saying that 1 over cos theta is sec theta. So if you are talking about 1 over B or A over B, definitely we are going to have what? B over what? A. And we are saying that 1 over tan theta is going to give us cot theta. So if you say 1 all over C over A, you are going to get A over C. When we looked at these reciprocals, we said one more thing. And that one more thing we said is, let us see whether we can get the ratios of these basic trigonometric functions by saying sin theta all over cos theta. What are we going to get? When we said sin theta all over cos theta, we evaluated it and we noticed that tan theta is the same thing as sin theta all over cos theta. We equally said cos theta all over sin theta, we evaluated it, we came to know that cos theta is the same thing as cos theta all over sin theta. So with this in mind, we go into what we call trigonometric identities. There are three basic trigonometric identities that we should be looking at. The first one is called the Pythagorean identities. They are three in number. The Pythagorean identities. That is what we are going to look at today to see whether we can prove the Pythagorean identities. The next time we will be looking at what we call the sum and difference identities. And then maybe in our future class also, we look at what we call the double angle identities. So permit me to clean here while we now talk about the Pythagorean identities. Three of them. So I'll clean here. Okay. So let me clean this socatoire to call up what I have here and put on top of this board. What we have here is that sin theta is C over what? B. So I have that sin theta equals C all over what? B. What I have that cos theta is A over B. So I have cos theta equals what? A over what? B. And what I have that tan theta equals what? C over A. C over what? A. So with that, I will clean this place. So that we have a place to show this. The first Pythagorean's identity says that sin square theta plus cos square theta equals to 1. They ask us to prove it. So the first identity says, number 1, prove that sin square theta plus cos square theta equals 1. That is what they want us to prove. Then we begin. We already have everything on the board. So we ask ourselves, or we write solution. When they have sin square theta, it is the same thing like sin theta all square. So this can be written as this: sin theta all square. The sign here is what? Plus. Open the bracket. Here is cos theta all square. They say I should show that it is equals to 1. What is my sin theta from here? Sin theta is C all over what? B. So I will come in place of this and write what? C all over what? B. Open and close, all raised to power 2 plus. I come here. What I have here is cos theta. What is my cos theta? A over B. So I will write what? A all over what? B, all raised to power what? 2. They say I should show that it is equals to what? 1. C squared, that is C raised to power 2 means what? C squared all over. B raised to power 2 means what? B what? Squared. The sign here is plus. A raised to power 2 means what? A squared all over. B raised to power 2 means B what? Squared. They ask me I should show that this is equals to what? 1. We are together? Then, what's the LCM of B squared and B squared? LCM of B squared and B squared is B squared. So you open a bracket or you have a line this way. You write B what? Squared. B squared divided by B squared, 1. 1 times C squared plus. B square divided by B square, 1. 1 times A square, A what? Square. They ask me to show that this is equals to what? 1. But do remember something that Pythagoras said in the right angle triangle. Pythagoras said that the square of the hypotenuse is the same as the sum of the squares of the opposite and the adjacent. Let me draw and show you what I mean by this statement that is accredited to Pythagoras. He said that when you have a right angle triangle this way, this is a right angle triangle. Here is my A, here is my B, here is my C, here is this. And you have here to be A, you have here to be C, and you have here to be B. Here is what we call the hypotenuse. Here is what we call the opposite. Pythagoras said that the square of the hypotenuse, which is B squared, he said that B squared is given as C squared plus A squared. That is, the square of the hypotenuse is the same as the sum of the squares of the opposite and the adjacent. So B squared is the same thing as C squared plus A squared, according to Pythagoras. So by implication, B squared, C squared plus A squared can be used interchangeably. Anywhere I see B squared, I am free to use C squared plus A squared, and anywhere I see C squared plus A squared, I am free to use D squared. Then I return back here. What is the numerator here talking about? The numerator here is talking about C squared plus A squared. And I have already established here that C squared plus A squared is the same thing as what? B squared. Therefore, I can let go of this C squared plus A squared and use in place of that what? B squared. And what I have here becomes, the numerator becomes what? B what? Squared all over. What I have in denominator before is what? Is B what? Squared. I was asked to show that this is equals to what? 1. And of course, when you cancel B squared is 1, you cancel B squared is 1. And 1 divided by 1 is what? Is 1. And by that, you have proven the first identity of the Pythagoras that says that sine square theta plus cos square theta is equals to 1. We have established that one. Okay? I really want to believe that I have not had too much of a problem. If you have, please make effort to drop your worries in the comment section so that we can come to your aid the moment we come across such questions or such worries. Okay? So how are we now going to establish the two remaining identities of Pythagoras? They are established simply by dividing the first identity with either the cosine or either the what? The sine. So this is the first identity proven. So we want to go and establish the second identity. That's what we intend to do, to establish the second what? Identity. How do we establish the second identity? Watch what I'm going to do. So I'll clean here. What we do is to come here. Let us first of all now, this is now, we are talking about the second identity of Pythagoras. So I am going to first of all divide all 2 with the sine theta. After which I divide 2 with what? With cos squared theta. So first of all, I am trying to divide with the sine squared theta, which is the second identity of Pythagoras. So that is going to be proving the second identity of Pythagoras. I have sine square the theta, which is what I have here, plus cos square the what? Theta equals what? 1. dividing all through with sine squared theta. I have all over sine square theta, then plus cos, sorry, all over. I'm dividing through with sine, all over sine square theta, all over sine squared theta. That is using sine squared theta to divide all through the first identity of a partographs. So this will cancel this. I have 1 plus. There is square here. There is square here. So I can now write both of them and then square them all together. So this is the same thing like saying plus. I have cos theta all over sine theta all raised to power what 2. This is equals. Remember that we have that 1 over sine theta. Where do we have it? That 1 over sine theta. We earlier told us ourselves that 1 over sine theta is cosec theta. But what I have here is 1 over sine theta squared. So 1 over sine theta squared is going to be cosec square theta. So what I have here, it becomes what? CSC squared what? Theta in place of this. Then we return back. Here is my 1 plus. Do remember that cos theta all over sine theta. Where is it? Cos theta all over sine theta is cot theta. So in place of this, I can write what? Cot theta. And that means that I'm going to have cot square theta. So here becomes what we call cot squared what? Theta equals C SC squared theta. This is the second identity of partographs. So somebody can ask you in the exam to prove that this plus this is equals what this. Just remember for yourself this, which we have established and proven. Divide it all through with what? Sine square theta. Get a values like this. Raise values with this thing which we have proven earlier. And then this thing comes out very clearly. Very, very clearly. So that is all about this. How do we establish the third identity? How do we establish the third identity? We are going to establish the third identity by dividing the first identity all through with cos square theta. Because what we did here was to divide all through with sine square theta. So permit me to do this, knowing that you know that this is the first identity of partographs, this is the second identity of partographs. So let us look at establishing the third one. You permit me to clear. What we have here becomes that I have sine theta squared plus cos theta squared is given as what? 1. So I'm going to say all over cos squared theta plus all over cos squared theta all over cos squared theta. What did I do? To divide all through with cos squared theta. So in that case, cos squared theta will cancel cos squared theta, and I have this and this. So this is 1 and this is 1. And 1 divided by 1 is what? Is 1. Then I come here. I will have that sine theta all over cos theta all raised to power what? 2 plus 1 divided by 1 is what? 1. This is equals. We told ourselves earlier that 1 all over cos theta is sec theta. But we are now saying 1 over cos square theta. So it becomes what? Sec square theta. So this now becomes what? Sec square what? Theta. Okay? So what do we do when we come here? Of course, we now come and begin to look. Here is sin theta all over cos theta. And we know that sin theta all over cos theta is tan theta. Is tan theta. So what do? We come here and then we write that in place of this sin theta over cos theta, I'm going to write what? Tan theta. So I have tan theta. But because of this square, I'm going to write tan square theta, just like the way I've been writing these words. Then plus 1 equals sec square what? Theta. This is the third identity of partographs. That sec square theta is given as tan square theta plus 1. This is the first. You remember when we proved the other one. You understand? So what I want you to bear in mind is what we have today here on the board. Okay? Then these three partographs identities. Okay? Bear them in mind because in our subsequent classes, what we are going to do is we call them up now, we use it to solve a problem. We call them up now, we use it to solve a problem. Bearing in mind that you already understand where we are coming from. So most likely, this class will be tagged in YouTube Trigonometric Identity 1 or at a class on Trigonometric Identity 1 or Trigonometric Ratios 1. Thank you very much for coming around for our today's class. We still look forward of having you in our next class.